Okay, welcome to 1.2 Equations of Motion. Again, this should mostly be a review of things you've seen already. We're talking about the equations of motion, and we want to get equations that are going to relate all of the different variables that we have: acceleration, initial speed, final speed. So we're going to see how we can get those equations. We're going to start with average acceleration, and we know that our equation for that, the sort of default equation, is that the average acceleration is equal to delta v over delta t. We can expand that a bit to say it's vf minus vi over delta t. And again, we're talking delta v over delta t. That's the same as saying the slope of a velocity time graph. And I'm just writing vt for velocity time. What is a velocity time graph? Well, it's what we see on the right here. It's just a graph where we plot velocity versus time. So you can see on the graph to the right here, we have velocity versus time, and you can see that we have our initial velocity and our final velocity. And if we got the slope there, well, we're looking at vf minus vi divided by delta t. That's the slope of our graph. So that's our acceleration. But the other piece of information we can get from that graph is displacement. And we can do that by taking the area under the graph. Now that's always true because velocity is the derivative of displacement. We can go backwards, we can find displacement by taking the area under the graph. So if I have some way of finding out what this area is, including this bit here, that'll tell me the displacement. And the way we can do that is we can say, well, that's going to be the area of this rectangle plus the area of this triangle. Another way of looking at that is to say it's going to be the area of, well, the rectangle is solid this whole way. This triangle is equal to half of the total area of this top block. So I could divide that in half another way. I could divide it like this, where that's the average between initial and final velocity. So if you follow that, then great. If you're not sure, well, the equation for that looks like this. We can say that the displacement, by taking the area under that graph, is equal to 1/2 of vf plus vi times delta t. So basically what we're saying is we're taking the average of these two values and sort of creating a graph that looks like this, and then finding the area under that graph. That gives us the area. Okay. So now we have two equations from this graph. We have an equation for displacement, a displacement for acceleration. We're going to put those together now. And with those two equations, we can work out all our other equations. So here it says solve the average acceleration equation for vf, then substitute that value into the displacement equation above and simplify. So this average acceleration equation, we're going to rearrange for vf. So here I've got, well, I'll start with A average equals vf minus vi over delta t. And now I will rearrange that for vf. So that looks like vf is equal to A average delta t plus vi. Okay, so now we have an equation for vf, and the instructions said we want to put that now into our displacement equation. So let's just do that here. We've got displacement. That's 1/2 vf plus vi delta t. And we'll put in now our value for vf. So this looks like A average delta t plus vi. And then we have plus vi again from the equation above. All of that times delta t. Now I'm just going to expand and simplify this thing. So I have 1/2 times A average delta t. And then I have 1/2 times vi plus vi. So 1/2 times 2vi, this just becomes vi. And all of this again is being multiplied by delta t. So I'll give one more line here, 1/2 A average delta t squared plus vi delta t. And there we go. Now we have an equation for displacement that doesn't involve the final velocity at all. So that's one of our 5 special equations. We have equations, we have one equation here, a second equation here. We just created a third equation. Equations 4 and 5 we can create sort of in the same way. But it's important that you sort of see how we can derive these equations from each other. Okay, that said, that's one of our equations. We're going to just look at this table now, which has the 5 special equations that we use for kinematics. Okay, so what we did above was just to find out where this equation comes from. Okay. So you can see those equations in this table, and the important thing about this set of equations, you probably remember them from last year, but they're all different ways to solve kinematics problems. And you see that each one of them has 4 variables. And they have a different set of 4 variables, because we have 5 different variables total. Each one only has 4. So I want to summarize that in this table here. You can see this first equation has displacement, it has final velocity, it has initial velocity, and it has time. But it's missing acceleration. And likewise, the second one, we have final velocity, initial velocity, acceleration, and time. But in this case, we're missing displacement. You can see that each one of these, I'm not going to go ahead and write down all the variables that are in them. The more important thing is to see what's not in each of those equations. That one is missing VF, this is missing VI, this is missing delta t. And this is useful because it means that on a problem, if I have 3 variables and I'm trying to solve for a 4th, I just look at all of those and I say, what am I missing? Maybe I don't care about final velocity at all. Then I use this equation because it doesn't use final velocity. Maybe I don't care about time. Well, then I use this equation because that variable doesn't use time. That's how we use these equations. Okay. We're going to go on to the next page and actually solve a few problems using these. The first one says, 2 cars are at rest on a straight road. Car A starts 120 meters ahead of car B, and both begin moving in the same direction at the same time. Car A moves at a constant velocity of 7 meters per second forward. Car B moves at a constant acceleration of 2 meters per second squared forward. So car A is moving at a constant speed. Car B is accelerating. Calculate how long it will take for car B to catch up with car A, and calculate the 2 velocities of the 2 cars when they meet. Okay. Like always, for physics problems, it's a good idea to draw this first. So I'm going to draw a little picture of what's happening. So let's see, I've got my car. I'm going to call this sort of my 0 position. And it tells me that car A starts 120 meters ahead of car B. So I'm going to say that car A starts all the way over here, and I'm going to draw a little car. That's my little car. That's car A. And it starts over here at 120. So car A has already started over at 120 meters, whereas car B starts at 0. So I'm going to put this car B right here, so that its front is right at 0. Okay, now we know that car A is moving at 7.0 meters per second forward, and car B, well, I'm just going to sort of change where I have this 120. We'll say that this was 120 meters here. Okay, and so car B, car B is moving with no initial speed, but it is accelerating at 2.0 meters per second squared. Okay, so now we have some bits of information. The question is, where are they going to meet up? Where are they going to have the same displacement? And so we actually have two sets of equations here. We can talk about car A's displacement, and we can talk about car B's displacement. And we say that at this point here, displacement A is going to equal displacement B. Equal the displacement. Let me just fix that there. Oh dear. Okay, so at this point, displacement A equals displacement B. At that point. Okay. So let's figure out displacement A first. It's moving at a constant speed, and it starts at 120 meters forward. So it already has an initial displacement of 120 meters. Hopefully that makes sense to everyone. It starts at 120 meters, and then it's going to be moving at 7 meters per second. So we're going to say 7.0 times delta t. Because every second it's going to move forward by 7 meters. Okay, and then we want to find the displacement B. Well, that's going to be equal to, it doesn't have any initial displacement. We're going to use one of our equations, one of our kinematics equations. And if we flip back to the previous page, what do we know? We know the initial velocity is 0. We don't know anything about the final velocity. So that means we're going to pick this equation. Because we don't know anything about final velocity. We're not really concerned with it yet. So, this equation here, delta d equals vi delta t plus 1/2 a delta t squared. So vi delta t plus 1/2 a delta t squared. Okay, we have this equation. We can fill in some of the values here. Well, vi is 0. So that means that that whole first term disappears. We get here just 1/2 a. A is 2.0 meters per second squared times delta t squared. And there we go. Now we have two equations that are equal to each other. So if I take all this, this tells me that 120 plus 7.0 delta t is equal to, well, 1/2 times 2, this is going to be 1, or it's just going to equal delta t squared. And then what we can do is just divide, well, actually we're going to have to factor this guy here. So we'll bring this all up onto the same side here. This gives me delta t squared minus 7.0 delta t minus 120 equals 0. Okay, and now we're going to see some factoring. Hopefully you remember your factoring from previous years. We want two numbers that are going to add up to -7, multiply to -120. And I'm going to leave that to you to work out on your own. I'm just going to put the answer. So if you want to take a break and try to work that out, go for it. But the answer here is delta t plus 8, delta t minus 15 equals 0. You see that those 8 and -15, they multiply to -120, add to -7. If you're having trouble with factoring, please talk to me and I can help you out. Okay, that means that there's two possible solutions here. Either delta t is equal to -8, or delta t is equal to 15. The last step here is to say, well, this is impossible. Because we're talking about what happens after the race starts. -8 is going backwards in time. That doesn't make too much sense. So our answer there is going to be 15 seconds. So we can say, therefore, delta t equals 15 seconds. And if you haven't seen this before, these three dots, those three dots mean therefore. And generally, I would like to see that every single question that you answer, you finish with a therefore statement. And it can just be as simple as this. You just put the three dots and then your final answer. Great. Okay, I want to point out one other thing, which is that your document might look a bit different from the one I have here. I've rearranged things a bit, but the document I gave you might already be the older version. So sorry about that if it looks a bit different. Okay, but we're on to the next question here. It says a motorcyclist drives along a straight road with a velocity of 30 meters per second forward. The driver applies the brakes and slows down at 5 meters per second squared backward. Now we want to calculate the braking time. Okay. Well, first we want to say, what do we know? And I'm going to show you a method that you can use to solve this. It's called the GRESS method. G-R-E-S-S. Okay, and this stands for given, required, equations, solution, and statement. Okay, and this is just a sort of a formal way to lay out the solution to a problem. I don't require that you use this, but if you find that you're having any trouble, then it's not a bad way to go. So you start this method by just putting the letter G, and now we're going to list all the information that we're given. So we're given the fact that the initial velocity equals 30.0 meters per second forward. I'm just going to put an F for forward. We're given that the final velocity, while we're stopping, the final velocity is equal to 0 meters per second. There's no direction on 0. Okay, we're given that the acceleration is equal to 5.0 meters per second squared backwards. So I'm going to put the letter B there. And that's what we're given. Now, I'm just going to rewrite this acceleration here. 5.0 meters per second squared backwards, that's negative 5 meters per second squared forwards. And that's just going to make our math easier if I put everything in the same direction. We're done listing our given. Now we look at required. So the R is for required, and it just says, what do we want to find out? We want the braking time, so we want delta t. Good. Now we list our equations. That's under E. What equations are we going to use? Well, we've got VI, VF, A, delta t is what we're solving for. So that means we're just missing displacement. We don't care about displacement. So we want to use, going back to the previous page, we want to use the equation that doesn't have displacement in it. This one. Okay, so I'll go back over here and use that equation. My equation is VF equals VI plus A delta t. And I'll just say right now that that list of equations that I just showed you on the previous page, you will have that on tests. You will have that list. You do not need to memorize those. So really it's just a matter of knowing which one to use. Okay, so we have our equation. Now we do our solution. And our solution looks something like this. I will rearrange that equation above to solve for delta t. So delta t equals VF minus VI over A. Good. And now we'll plug in some values. VF was 0, minus VI is 30. Divide this by negative 5, and that gives me, so 0 minus 30, negative 30 over negative 5, that gives me 6.0 seconds. Good. And then the very final step is my statement. So I can say, therefore, the braking time is 6.0 seconds. And I'm going to say it's a good idea to have this sort of a statement with words and everything. Therefore, the braking time is 6.0 seconds. If you just write, therefore, delta t equals 6.0 seconds, I will accept it. All right, we're on to the last page here. Now we want the braking distance. And braking distance, well, that's also going to be our displacement. So how far do we move while we're braking? And we can sort of use the same method here. So we're given the same pieces of information as on the previous page. I'll just write those out again here. So given VI equals 30.0. Okay. And we'll just go on. Negative 5.0 meters per second squared forwards. Required. This time we want to find displacement. Notice that I didn't list the value that we just calculated as part of my given. I'm going to avoid using that one because I might have done something wrong. I don't really know. It's always safer to use the values that were given to me in the problem if I can. And in this case I can. Because I have an equation that doesn't have delta t in it. I'll go back to my first page. This one doesn't have delta t. That's the equation that I'll use. Okay, so going back to page 3. My equation, displacement equals Vf plus Vi over 2 delta t. So that's just finding sort of the average velocities. Okay, now we want to do our solution. Delta t equals, so again oops, not delta t, I'm sorry. I was looking at the wrong spot here. So my solution here is just the equation that I put above. I'm going to start filling in the blanks. So brackets, we've got 0 meters per second for Vf. Vi is 30. My 2 on the bottom, and then I multiply by the elapsed time, which was oh, and I'm sorry, I've put the wrong equation because I've put an equation that uses delta t. So I want to go ahead and just fix that right away. I feel bad about that. I went and used the wrong equation. Okay. We want the equation for displacement that doesn't have time. Vf squared equals Vi squared plus 2a delta t. Vf squared equals Vi squared plus 2a delta d. Good. Now we're going to go ahead and do this. So I'll rearrange for delta d. This is going to be like this. And now I can fill in some values. 0 squared minus 30 squared over 2 times negative 5. So this gives us negative 900 over negative 10, which is going to be equal to 90 meters. And again, I need to put my direction in, forwards, and there we go. Okay, there's my final answer, and now I just put my statement. Therefore, the braking distance is 90 meters forwards. Okay, good. There's just one last little topic here. I'm sorry for the length of this. This is not, I usually try to keep the videos to a shorter length than this, so I'm sorry this one has run on a bit. Okay, but we're on to the last topic here, free fall. So free fall is the motion of an object where the only force is gravity. And you might remember that the force of gravity is equal to mg, where g is equal to 9.8 meters per second squared. Okay, so we're just going to quickly look at how our kinematics equations apply to free fall. This says a ball is thrown from a height of 52 meters from the top of a building with a velocity of 24 meters per second straight up. So it's thrown straight up from the top of a building. Determine the velocity of the ball at ground level. So if I draw a little picture here, I'm going to say that I'm on top of a building and the ball is thrown straight up at 24 meters per second. And this ball has some height of 52 meters to start with. Okay, and now it's just a kinematics equation. We know that, so if I'm listing my given values here, we know that VI is equal to 24 meters per second up. We don't know about VF. That's what we're going to try to find. Let's see. We know delta D. This is going to be equal to 52. Sorry. Okay, displacement is going to equal 52 meters down, which is the same as saying negative 52 meters up, because we're saying that the ball ends up on the ground, so it needs to go down 52. And we know that the acceleration is equal to, I'm going to jump straight to the up, so negative 9.8 meters per second squared in the up direction. Right? It's positive in the down direction, which means it's negative in the up direction. Okay, so those are our given values. Required, we want to find VF. And our equation for this, we've got VI, VF, delta D, A, so there's no delta T. So our last equation, VF squared. VF squared equals VI squared plus 2A delta D. So VF is going to equal the square root of, and now we've got 24 squared plus 2 times negative 9.8 times negative 52. Take the square root of all of this, and our final answer is 40 meters per second in a down direction. Okay, so that's what we're looking at. Notice that with VF, when we take the square root can be either a positive number or a negative number. And I've said that it's negative because I've said it's acting downwards. There, you just need to use your logic to say, what direction should the ball be moving when it hits the ground? Because mathematically, that number could have come up as up or down. We need to use our judgment there. Okay, finally we make a statement, and I'm just going to do a really short statement here. Therefore, VF equals 40 meters per second down. Okay. One last bit here. How long does it take for the baseball to reach the ground? Or not the baseball, but for the ball. And what I'm going to do is leave that one for you to attempt yourselves. Make sure that you understand the process. I suggest setting it up as GRESS, G-R-E-S-S. But if you don't want to use that method, that's fine, as long as you get to the right answer. So go ahead and try that one. Try the homework problems there, and I'll see you in the next lesson.